Now let us derive an expression for the current in a purely inductive circuit. Suppose we have an inductor of inductance, let's say L, connected across an AC source like this. We know the EMF of an AC is always V equal to V0 sine omega t. Here V0 is the peak voltage, omega the angular frequency, and t is the time. Here L stands for the inductance of the coil. Let at any instant this be the, let's call this loop as A, B, C, D. Let at any instant this side be the positive polarity and this side be the negative polarity. We know due to the change in flux, an EMF is induced in the inductor. We have the EMF induced in the inductor. Let's represent that as VL is equal to, we have this expression L di by dt. We actually have to derive this expression, but in this derivation we just take VL is equal to L di by dt. We can derive the expression in the video later. Now let's consider the EMF induced across the inductor is L di by dt. Let's call that as equation number 1. But according to Lenz's law, the EMF induced in the inductor always opposes the source EMF. So if this is the polarity at any instant across the source voltage, the polarity formed across the inductor will be like this, because this positive polarity of the source is repelled by the induced EMF, this positive polarity of the induced EMF. Induced EMF formed will always oppose the source EMF. That is in accordance with the Lenz's law. Now we can apply the Kirchhoff's law across the loop A, B, C, D. So let's consider the loop A, B, C, D, A. Let's take this loop. Let the current formed will be I. Since this is the source EMF, the current always moves from positive to the negative side. Now we are going in this direction from A to B, then from B to C, C to D, and D to A. Now by Kirchhoff law we know if we move along positive to the negative side, that is in AB, we just have to take AB. In AB we are moving from positive to negative side. So we can take this as the negative voltage. So minus V. Plus there is no voltage in here in the branch BC. Now the voltage across CD, we are moving it from negative to positive. From negative to positive, we have to consider that as positive. So VL. Again, there is no EMF across DA. So by Kirchhoff law, we have the net EMF is 0. This is according to Kirchhoff's loop rule, or you can say Kirchhoff's second law. Now we have the EMF induced VL is equal to V, and we can substitute the value of VL, that is L di by dt is equal to, we can apply V0 sine omega t here. V0 sine omega t. Now taking L and dt to the right side, we have di is equal to V0 sine omega t dt divided by L. Clear? Now let me erase this. Now to get the total EMF, the total current, the total current, that is, in order to get I, we have to integrate this equation. So integral di. So I is equal to integral of di is V0 sine omega t dt divided by L. I is equal to, we know V0, the peak EMF, and inductance are constant. So you can take that out of the integral sign. Integral sine omega t dt, which is equal to V0 by L. You know the integral of sine is minus cos omega t. Minus cos omega t by omega. We have to write omega because, and now a constant sign c. See, we have integral of integral of sine ax, where a is a constant, is equal to minus cos ax by a plus some constant c. I just applied this formula in here. So integral of sine omega t is minus cos omega t divided by omega. Now simplifying this, you will get I is equal to, again we can write this omega and L together. So V0 divided by omega L. Let's put minus sign in here. Cos omega t plus c. Clear? Or let's write the negative sign here itself. Okay. Now, how can we rewrite this minus cos theta term in terms of sine? We know sine 90 minus theta is equal to cos theta. Sine 90 minus theta is cos theta. If you multiply negative to both the sides, and this negative goes to inside of the sine, because sine is an odd function. So sine, you can write minus of pi by 2 minus theta equal to minus cos theta. So sine of this is equal to theta minus pi by 2. That is minus cos theta. So we have sine theta minus pi by 2 is equal to minus sine theta. Here actually we have sine minus theta equal to minus sine theta. So this minus will go into the inside of the sine function. So we can write here I is equal to V0 by omega L. Instead of minus cos theta, minus cos omega t, you can write sine omega t minus pi by 2 plus c. Clear? I just used this equation in here. Now we have to find the value of the constant c. Now we want to find the value of c. For that, let's take the initial case, that is when voltage equal to 0. Initially, the voltage, that is when no AC source is provided to the inductor, which means when V is equal to 0 implies the maximum EMF is also 0. So this term will become I is equal to, this whole term will be 0 because since V0 is equal to 0. So 0 plus C. So I becomes C. Initially, since there is no source EMF, so when there is no source EMF, there will be no peak voltage, which means the source is not connected to the inductor. That means basically there is no current to the inductor. Since there is no source, there will be no current to the inductor. So I is equal to 0 when V equal to 0, which basically means the constant of proportionality C is also 0. So you can write I is equal to V0 divided by omega L sine omega t minus pi by 2. So this is the expression for current in an inductive circuit. Clear? Now let us compare the phase of EMF and voltage. We know the source EMF, source voltage V is equal to V0 sine omega t. Here the whatever be the function inside the trigonometric function, that is the phase of the function. Here omega t is the phase of the voltage. But we have I is equal to, we have V0 divided by omega L sine omega t minus pi by 2. Before saying about this phase, just introduce I0 in here. We can write this expression I is equal to, let's say, some I0 sine omega t minus pi by 2. Here I0 stands for V0 divided by, comparing this with this one, we have I0 is equal to V0 divided by omega L. Now let us consider the Ohm's law. We have current in the circuit is the voltage divided by resistance. When you compare the equation, this Ohm's law, with this equation, you know, here instead of R we have omega L. But here it is not the resistance, it is resistor, it is the inductor. So omega L is actually basically the resistance offered by the inductor to the flow of AC, similar to that of the resistance offered by the resistor to the flow of direct current. So we can write XL equal to omega L, where XL is the resistance offered by the inductor to flow of AC, and we can call that as inductive reactance. Clear? Inductive reactance. Or you can write XL is equal to, instead of omega you can write 2 pi f into L. We already discussed this. We have angular frequency is equal to 2 pi f. So comparing again, write this equation. We have V equal to V0 sine omega t, also I equal to I0 sine omega t minus pi by 2. So coming back to the phase, we have here the phase is omega t, here it is omega t minus pi by 2, which clearly indicates that current is behind the voltage. So current lags behind the voltage by a phase of pi by 2. Clear? That is current, or we can say voltage leads the current, or it is better to say current lags behind the voltage. That is when omega t is equal to, let's say, 270 degree, then for current the phase will be, this is for voltage, then it will be 270 minus 90, which is 184 volt for the current. Clear? The phase angle for voltage is 270, then phase angle for the current is 180, which is less than 90. Clear? Now we can draw the graph of both this voltage and current. We have Let's represent the x-axis with the phase omega t, and let's represent voltage and current on the same axis. Let this be the peak value of voltage V0, and let's write I0 the peak value of current. Similarly, there will be corresponding values in the negative axis also. So V0 and minus I0. Let's mark 0, 90, 180, 270, and 360. That means at one complete cycle, it means one full rotation, that is 270, 360, or in radians it will be 2 pi. Now we have V equal to V0 sine omega t and I equal to I0 sine omega t minus pi by 2. Now when omega t equal to 0, which means sine omega t is 0, that is V equal to V0. Sorry, V equal to 0. Or you can write V equal to V0 sine 0. Sine 0 is 0, so V equal to 0. That is when omega t is 0, voltage is 0. Let's mark voltage with the green color. And when when omega t is equal to pi by 2, we can write V equal to V0 sine pi by 2. You know sine 90 is 1, so V equal to V0. So omega t is pi by 2, then V equal to V0. Again, when omega t is equal to pi, we have V equal to V0 sine pi. Sine pi is again 0, so voltage is 0. Clear? Now, you can continue like this. When omega t equal to pi by 2, then sine 3 pi by 2 is minus 1, so it will be minus V0. Again in 2 pi, the value becomes 0. That is sine 2 pi is 0. So the graph of the voltage will be like this. So this represents the graph of voltage, that is V equal to V0 sine omega t. Now let us draw the graph of I equal to I0 sine omega t. Listen this part carefully. We have when I equal to, or let's say initially the omega t will be 0. When omega t equal to 0, we have I equal to I0 sine 0 minus pi by 2. Sine omega t minus pi by 2, which is, that is, let's mark the bracket in here. Sine omega t 0 minus pi by 2. So this is equal to I0 sine minus pi by 2. Sine of minus 90 is minus 1. So minus I0. That means when omega t is 0, we have a value of I which is equal to minus I0. So the graph of current starts from here. Now what happens when omega t is equal to 0? Sorry, equal to pi by 2. Clearly, I equal to I0 sine pi by 2 minus pi by 2. Sine pi by 2 minus pi by 2 is 0, sine 0 is 0. So the value becomes 0. So when omega t is pi by 2, the value of current becomes 0. What happens when omega t equal to pi? That is, when omega t is equal to pi, again if you substitute that in the equation, I0 sine pi minus pi by 2, this is equal to I0 sine pi by 2. But you know sine pi by 2 is 1, so its value will be I0. So when omega t is pi, its value will be maximum, I equal to I0. Now you can continue like this and you will get a graph like this. Clear? So this is the graph of I equal to I0 sine omega t minus pi by 2. Clearly, the graph from the graph itself, you know, it's not in the same phase. That is, suppose consider, let's take the value at omega t equal to 0, omega t equal to 0, the voltage is 0. But there is a value of current in the which is of peak magnitude in the negative direction. Clear? Now, how will you represent this in phasor diagram? Uh, I don't want to talk much about the phasor diagram. We will discuss that later. But phasor diagram basically means the phase difference, or it shows the phase difference between the voltage and current at any instant. So, so let's represent the phasor diagram. Suppose let's take this be the voltage. The phasor diagram simply represents the rotating phases. Let this be the peak value of voltage. Let it be at omega t. Clearly, you know the current lags behind the voltage. So the value of current will be, we take the clockwise as positive, anti-clockwise as positive. So the graph of voltage will be behind, so graph of current will be behind the voltage. So this represents the peak value of current. Clearly this angle will be pi by 2. That is, voltage is current is behind the voltage. See, this is the forward motion. So if voltage is here, if current lags behind the voltage, means current is behind the voltage. Clear?